Okay, so hello and welcome back. So in this video we want to basically talk a little bit about ellipses and talk about their equations, talk about the different characteristics that they have, and well, basically about the there was something else called there is something called the eccentricity of an ellipse. There is the equation of an ellipse. There is the latus rectum of an ellipse, and there is basically almost every basic thing that you need to know about these ellipses. So basically, an ellipse is, by definition, is basically some geometric or a conic section. A conic section, something like this. For example, suppose that you have basically, first of all, these ellipses have these axes, and these are all axes of symmetry. And suppose that you have, it's basically something like this. So it's basically not a circle, meaning that if you had a circle, you would have basically, you could imagine that a circle has two axes of symmetry, and these axes of symmetry are perpendicular, and the length of these two axes are exactly the same. So then if that's the case, then you would get basically a circle. But now suppose that one of these axes is longer than the other one, and then based on that you will get some conic section, which is called an ellipse. Now, since the two axes are basically of different lengths, then one of these axes, the longer one, has been called the major axis, and the shorter one has been called the minor axis. So the major axis and the minor axis. And by definition, basically it is basically such that an ellipse is created in such a way that, and something that I forgot to say is that there are 2 points on the major axis. I can call them, for example, F1 and F2, and these are at the exact same distance from this point over here, which is called the center of the ellipse. So this point over here is called the center, and this point over here is called the focus, and this point over here is also called the focus. And so basically we say that an ellipse has two foci. Foci is the plural form of focus. So we say that basically these basically an ellipse has two foci, meaning that two focuses, and so these two foci are at the exact same distance from the center, meaning that if you take this distance as C, this distance is also C. And where the definition of an ellipse is basically this: if you pick any point on the ellipse, meaning that this basically this curved path over here, this closed curved path over here. If you pick any point on here, call it, for example, P of P x comma y, then the distance of this point P to this first focus, and the distance of the same point P to the second focus, meaning that PF1 plus PF2. Now this distance is going to remain constant wherever you go on the ellipse, meaning that if you go over here, I will call this, for example, P1, and so this becomes P1F1, P1F1, and P1F2, and then I can pick another point over here, P of 2, which is, for example, again some x comma y, and then basically I will have these two distances relative to point P2. So then I can write, for example, P2F1 plus P2F2 is equal to P1F1 plus P1F2. And well, wherever you go on this, as I mentioned, wherever you go on this ellipse, the sum of the distances of any point from the two foci is going to remain constant. It's going to be equal to some constant. You can call it anything, but it is basically constant. It does not change. And that is the definition of an ellipse. So then as a definition, I can say that an ellipse is the set of all points, in a plane, the sum of whose distances from two fixed points is in the plane is constant. The sum of whose distances from two fixed points, these two fixed points, from two fixed points in the plane is constant. And the two fixed distances, the two fixed points, are called the foci, which is basically as I mentioned, the plural of focus, are called the foci of the ellipse. The foci of the ellipse. So this is the definition of an ellipse. Now the constant, which is the sum of the distances of a point on the ellipse from the two fixed points, is always greater than the distance between the two fixed points. So there is something over here that will of course help you in at least many of these exercises over here. And there is a note. It says that the sum of, let's say that, for example, you have this basically, let's say that you have this basically ellipse over here, and let's say you have a point over here P, and this is for example F1, and this is for example F2, and if you connect these points together, you have the sum of these two distances would be PF1 plus PF2, okay, meaning that this distance plus this distance. And of course we said that it's going to remain constant wherever you happen to pick the point P. This distance is going to remain constant. This sum is not going to change. Now the constant, which is the sum of the distances of the point on the ellipse from the two fixed points, is always greater than the distance between the two fixed points. So if I take, for example, suppose that I take this distance as C. So we said that this center over here is exactly between the two foci, meaning that this distance is actually equal to this distance. And so if I take this distance as C, this distance is also going to be C. So that means that the distance between F1 and F2 is going to be 2 times C. It means that F1 F2 is going to be equal to 2 times C, for example. If I take this distance as C, this whole distance is going to be 2C. And this distance over here is always going to be greater than 2C. And of course you can see it over here as well, meaning that it's easy to see that, because as you can see it is a triangle over here. You have a triangle over here, and any triangle that you draw, the sum of any two sides of any triangle is always greater than the third side, meaning that if I take this as A and this side as B, the lengths of these sides A, B, and C, A plus B is always greater than C, no matter which side you take as A, no matter which side you take as B, no matter which side you take as C, and no matter which sort of triangle you might have. Any sort of triangle, taking these letters in any sort of arrangement or combination or whatever you want to take any triangle, or you can say in any triangle, the sum of this is some theorem in geometry. I don't know when we have done this, but it was a few months ago. So, but of course not in these videos, of course. So in any triangle, the sum of any two sides is always greater than the length of the third side. And so based on this, you can always say that basically PF1 plus PF2 is always greater than the 2C, which is basically, and this 2C, what this is over here actually is actually the distance, is actually this over here is the distance between the two foci. So that is something that you can use in probably at least one or a few of these exercises that we will have over here. These are the kinds of things that we do need to know. And then there is something over here. This the midpoint of the two foci. this point over here, which is the midpoint of the two foci, or basically the midpoint of the line segment joining the foci, is called the center of the ellipse. This is called the center of the ellipse. And the line segment through the foci of the ellipse is called the major axis. We talked about that this axis over here is called the major axis. And basically the major axis is well, by definition, the axis on which the two foci lie, basically. Whichever axis, basically, on whichever axis the two foci lie, that axis is called the major axis. And then of course the other axis, which is perpendicular to the major axis, this axis over here, is called the minor axis. The minor axis. And basically, the line segment through the center and perpendicular to the major axis is called the minor axis, which is basically this line segment over here. The endpoints of the major axis are called the vertices of the ellipse. Now, since you have the major axis over here, the endpoints of the major axis that actually lie on the ellipse are called. This is called the vertex of. This is called the vertex of the ellipse. This is also called the vertex of the ellipse. So these are some words. I mean, this is some terminology that you need to know about these ellipses, and when we talk about them, we have to use this basic terminology in order to be able to talk about ellipses. So there is now in order to basically have some sort of standard over here, what at least in the text that we are working with, and usually wherever you go and deal with these vertices, these ellipses. So if you have an ellipse over here, and if this is your major axis, and if this is your minor axis, we did say that basically these the foci of the ellipse lie on the major axis. So let's suppose that, for example, this is F1 and this is F2. So and you do know that basically an ellipse is symmetric about, if you imagine that you have your ellipse in an xy plane, for example, this is the x-axis and this is the y-axis. Basically, based on the definition of ellipses, it just so happens that an ellipse is symmetric about the x-axis, and it's also symmetric about the y-axis, meaning that you would get something like this, for example, and it's going to be symmetric about or with respect to both the axes, something like this. Meaning that if you pick some point over here, for example, x comma y, then basically there you will find some other point over here. If this line is perpendicular to the x-axis, then you will find some point over here exactly on the ellipse, which is x comma negative y. If you have this point over here, x comma y, you will find you will find some point over here exactly on the ellipse, which is basically negative x, for example, comma y. If you have this point over here, negative x comma y, you will find another point over here on the ellipse, which has the coordinates negative x comma negative y. So that means that basically an ellipse, and this basically applies to any x and y. So what that means is that an ellipse is symmetric with respect to the y-axis, and also symmetric with respect to the x-axis. Now, since that is the key, I did forget why I was saying all of this. Well, I was talking about this because I wanted to tell you about some conventions over here that are usually used with these ellipses. Basically, the distance between, you know that basically the two foci are at the exact same distance from the center, meaning that if I take this distance as c, this distance is also going to be equal to c. And usually, I mean, at least in this text that we are studying here, basically the distance between the center and the foci is denoted by c, by the lowercase c. And then the distance along the major axis, and if I imagine that this is the end of the major axis and this is halfway through the major axis, this distance is denoted by a, meaning that, well, then naturally this distance would then basically be 2a. And if I imagine that this is one end of the minor axis, and this is halfway through the minor axis, then this distance is denoted by b, and so then naturally this distance would be denoted by 2b. So basically this distance is going to be, this distance over here would be denoted by b, and this whole distance from here up to here is denoted by a. So that's, and the center is usually denoted by O, because what we are doing here is usually we locate our ellipse at the center of the coordinate system, and the center of coordinate system is usually denoted by O. So the center is usually denoted by O. And so that's basically the whole story. Now, one thing that I forgot here is basically the distance between the two foci is then, of course, going to be 2c. C plus c is equal to 2c. Now, there is some relationship between this this distance over here, which is basically half of the major axis. This is half of the, I guess I should change this color. Half of the this distance over here, a, which is half of the major axis, is basically called the semi-major axis. It is called the semi-major axis. And this distance over here, which is half of the minor axis, this is called the minor semi-minor axis. It is called the semi-minor axis. Now there is some relationship between the distance between the foci and the center, between the semi-major axis and between the semi-minor axis. And that relationship is basically a squared is equal to b squared plus c squared. Meaning that if you take, it's just a squared is always equal to b squared plus c squared, which is this distance over here. Now, in case you want to know basically how we can come up with this relationship, basically it's not that complicated. So if you take for example, if you take this vertex over here, if you call it P, well, of course, P is a point on the ellipse, right? P is a point on the ellipse, and we said that basically if you have basically some ellipse over here, and if you have these major and minor axes F1 and F2 over here, and if you have some point over here, this distance basically, for example, PF1 plus PF2 is going to remain constant, no matter where you basically pick this point P. So then if I take the point P over here, and if I have my foci over here as F1 and F2 over here, then of course I can write PF1 plus PF2, PF1 plus PF2, that is the sum of the distances of the point P. This would be the sum of the distances of the point P to the two foci. And that is basically equal to so basically you have PF1 plus PF2, so you can break down this distance as so PF1 basically would be this whole distance over here from P to F1. So, and PF2 would be this distance over here. So I can write this as F1O, this point is O. I can write this as F1O plus OP plus OP. So F1O plus OP is basically equal to PF1, and PF2 is basically this whole distance OP minus F2P plus OP minus F2P. Now OP is equal to C. OP is equal to C here, and this is also equal to C here. F1O is equal to C plus A. You see that F1O is equal to C. And well, F2P is basically this whole distance minus this distance. I'm sorry, F2P is basically this distance over here, which is basically A minus C. This distance is A minus C. So I can write here minus a minus c. So I can write this as 1, 2, 3, and 4. 1, 2, 3, and 4. So you have basically c plus c minus a plus c, which doesn't make any sense. Let me see. F1O is basically, so F1O plus OP is basically a plus c. No, let me write it this way. I'm sorry. I don't want to confuse you. But F1O plus OP is basically this whole distance over here. So I can write it as a plus c. A plus c. That is F1O plus OP. And I need to make some changes over here. Let me write this again. So I can write this as PF1 I can write as F1O plus OP. This thing over here I can write F1O plus OP. And then you have over here you have F2P, right? So now F1O plus OP is basically this whole distance over here, which is a plus c. So this is a plus c. And F2P is basically this distance over here, which is a minus c, plus a minus c. So then you can cancel these two out, and then you will be left with 2a. Now this is important. And what that means is that any point, and of course P can be regarded as any point on your ellipse, meaning that the point can be over here, it can be over here, it can be anywhere on the ellipse. Any point that you pick on your ellipse, and for example, let's suppose that you pick this point over here, and you would have these two distances over here. Let's say that your P is over here. So then the sum of these two distances again would be PF1 plus PF2. And this distance is always equal to 2a. So that is basically one thing here. Now if you take some point at one end of the minor axis, let's say for example Q over here. Now the sum of the distances, let me use another color over here. So let's say that I take this point Q over here, and the sum of the distances of this point to the foci would be F1Q plus F2Q. F1Q plus F2Q. And of course, if you take a look at this, if you take a look at this figure over here, you can see that F1Q and F2Q, basically you have these two triangles over here. You have this triangle over here. For example, this triangle over here, this side of this triangle is C, this side is B, and you want to find this side over here. So, and this is a right triangle. So if you have this right triangle, and this side is C, this side is B, and you want to calculate this side, of course this side is going to be basically, if I call it x for example, x is going to be equal to b squared plus c squared. Of course x squared is equal to b squared plus c squared, based on the Pythagorean theorem. and so x would be equal to the square root of b squared plus c squared. B squared plus c squared. So that means that f1q is actually equal to basically the square root of b squared plus c squared. And by the same logic, again, f2q is going to be the square root of b squared plus c squared. So I can write here basically this is equal to basically the square root of b squared plus c squared plus the square root of b squared plus c squared, and that is equal to 2 times the square root of b squared plus c squared. Okay, so that is again another point. That is again another point that we picked somewhere on the ellipse, and that is the sum of the distances of that point from the two foci. And we calculated that distance to be 2a, and for the same distance, now we got basically this expression over here. So that means that I can write 2a is equal to 2 times the square root of b squared plus c squared, and if I cancel out these 2's, I get a is equal to the square root of b squared plus c squared, or I can raise both sides of this equation to 2. I get a squared is equal to b squared plus c squared, and that is the relationship that basically we had over here. So a squared is equal to b squared plus c squared, and so you can, from this you can calculate many things. For example, if a squared is equal to b squared plus c squared, then you can say that, for example, b squared is equal to a squared minus c squared, or c squared is equal to a squared minus b squared. And then, of course, based on this, you can say that b is equal to the square root of a squared minus c squared. Let me write this properly. Based on this, you can say that b is equal to the square root of a squared minus c squared. Or over here, you can say that, for example, c is equal to the square root of a squared minus b squared, and so on and so forth. Based on your needs, you can use this relationship over here, but it is essentially this thing over here, which is a squared is equal to b squared plus c squared. And you need to know, of course, what a, b, and c refer to. A refers to the semi-major axis. B refers to the semi-minor axis, and C refers to the basically C refers to the distance between one of the foci and the center. So that is basically the relationship between the semi-major axis, semi-minor axis, and the distance of the focus and the center of the ellipse. Meaning that this is the relationship between the semi-major axis, semi-minor axis, and the distance between the focus and the center of an ellipse. And that is basically a squared is equal to b squared plus c squared. Now there are two basically special cases of ellipses that we will discuss as well, and then we will talk about the eccentricity of an ellipse. Okay, so now there are some special cases of these ellipses, which are, of course, they are interesting. These special cases are so basically we got this equation over here, which was basically a squared is equal to b squared plus c squared. A squared is equal to b squared plus c squared. And so if you take if you rewrite this equation as c squared is equal to a squared minus b squared, now if you keep this a, if you keep a fixed and vary c from 0 to a, and vary c from 0 to a, meaning that suppose that you have this ellipse over here, and you keep your a fixed, meaning that you don't change your a over here. Your a is basically this distance over here. You keep this fixed, and basically c is the distance between, for example, f1 and f2, and your b is basically this distance over here. Suppose that b is this distance over here, and this distance over here is c. Now you want to basically you want to vary, you want to keep your a constant, or basically keep your a fixed, but vary c from 0 to a, meaning that your c goes from over here, this distance, for example, let's suppose that this is c, and the more that you basically, and this is the center, the more that you get this closer to the center. And basically, if f2 was over here, then c was basically equal to 0, meaning that c is equal to 0 if basically f2 and O, for example, are the same points. And c is equal to a if f2, for example, and of course f1 is going to change respect accordingly as well. If f2 is if f2 f2 and, for example, let's call this point B, for example, and B are the same points. So if that's the case, so now if your c is equal to 0, that means that this basically this point f2, this what do you call it? This this point comes over here and becomes 1 with O, and this point comes over here and becomes 1 with O. So what that means is that then you would get a if c is equal to a, then in this equation you would get, in this equation, if c is equal to 0, then that means that 0 is equal to a squared minus b squared. That means that a squared is equal to b squared, and if a squared is equal to b squared, that means that a is equal to b. Now this distance over here is a, and this distance over here is b. So if a is equal to b, then what that means is that you will get a circle. You will get a circle. So that's basically if your c is equal to 0. Now if there is one more case over here, that if c is equal to a, basically if c is equal to a, then in this equation c squared is equal to a squared minus b squared. If c is equal to a, then this c squared becomes a squared, which is equal to a squared minus b squared. And so you can imagine that this point goes all the way up to b, and this point goes all the way up to here, and so basically you can cancel these two out. Negative b squared is equal to 0, and so that means that b is equal to 0. Now if b is equal to 0, your basically your ellipse becomes just a straight line with basically with the two foci at the end of this line. This becomes, for example, f2. This becomes, for example, f1, and this point, this is O, and that is basically what you get. So then you can say that your ellipse basically reduces to a line segment, f1, f2, joining basically the two foci. So these are the two extremes of basically, these are the two extremes of basically the two special cases that can happen in case of an ellipse. Either you will get a circle if your foci go all the way up to the center, or if your foci go all the way up to the endpoints of the major axis, then you will get a just a line segment basically. Okay, so far we have no problems. Now let me create another layer over here. 279, 280, 280, and then there is another basically concept over here, which is called the eccentricity. The eccentricity of an ellipse. We have the eccentricity of an ellipse. So basically the eccentricity of an ellipse is the ratio of the distances from the center of an ellipse to one of the foci and to one of the vertices of the ellipse. Meaning that, of course, the sentence is not very easy to understand, but suppose that you have for example, an ellipse like this, and you have f1 over here, you have f2 over here, and let's suppose that this is your ellipse. Now the eccentricity is just a ratio, and it is denoted by E. It's just a ratio of basically C to A, meaning that let's suppose that, for example, C was basically this distance over here is A. This distance over here is B, and C was basically this distance over here. This distance over here is C. Now basically the ratio of C to A, so this is C, and this over here is A. So the ratio of C to A, which is always basically less than or equal to 1, because C cannot be greater than A, but it is always less than or equal to A. So C to A is basically called the eccentricity of an ellipse. So then, since the focus is at the distance of C from the center, the focus is at a distance of C from the center. In terms of eccentricity, the focus is at the distance of AE from the center. This sentence is important, and it's going to be used in the rest of the work that we are going to use. So basically, I can say that then, since the focus, which is this point over here, f1 for example, since the focus is at the distance of distance of C from the center, then in terms of eccentricity, I can say that basically based on this equation, I can say that C is equal to AE. So in terms of eccentricity, the focus is at a distance of AE from the center. Okay, basically these sentences, you do need to break them down, and sometimes you even have to write them down, and you have to basically break them down logically, draw some diagrams for yourself so that you can understand them. But ultimately, when you do so, when you break them down logically, draw some diagrams and spend some time on them, then of course they're basically easy to understand. Of course, they need some time sometimes. So this basically over here is basically all. It's just a definition, which is called the eccentricity of an ellipse. Now the next thing that we have here is basically about the standard equations of an ellipse that I think we will do in the next video, because we will run out of time in this video. So I'll see you in the next video with the rest of these concepts. Thank you.